Hi, my name is Angela Capel from the Technical University of Munich, and I'm going to talk today about a paper in collaboration with Andreas Blum from the University of Copenhagen, named A Strengthened Data Processing Inequality for the Belafkin-Stachewski Relative Entropy, which has been published in Reviews in Mathematical Physics. The outline that we are going to follow today is the following. So first, we will start with some motivation to the problem, and for that we will review some similar problems that have been addressed in the past for the relative entropy. After that, we will move to the principal definitions that one needs to understand this problem. So first, we will review some notions and some properties of this Belafkin-Stachewski relative entropy, and after that, we will move to the results that we proved in this paper. Finally, we will conclude with some future work. So to start with, let me recall the well-known relative entropy for two positive states on a matrix algebra, which is given by this expression written here. And this is just one possible extension to the quantum setting of the traditional classical relative entropy. And another way to extend it quantumly, since now the states don't commute anymore, it's in what is called the BS relative entropy, or we would just name it BS entropy for short, which is given by this expression here. So of course you see that if everything commutes here, we obtain the same expression from the relative entropy and from the BS entropy. But in general, if they don't commute, we always know that the BS entropy is greater than or equal to the relative entropy for the same states. As I said, we are going to first present some well-known results for the relative entropy. So first of all, we are going to consider a quantum channel, which is nothing but a completely positive trace-preserving map. And for this quantum channel, we know that the data processing inequality holds, which essentially says that if we apply a quantum channel to both inputs of the relative entropy, we obtain something that is always less than or equal to the quantity that we had at the beginning. And since the 1986, we know that there's equality in this data processing inequality if and only if the first state can be recovered from the second state by means of something that is called a recovery map. And in particular, Petz showed that one can consider this recovery map written here, which of course was named Petz recovery map after him because of that. Now, if we focus on the particular case of a tripartite space HABC, and we consider as our quantum channel the partial trace in one of them, for example in A, now we can consider the case in which we are just grabbing two states with support in ABC, and we are going to denote rho BC as the state rho ABC after tracing out A in this state. So it's essentially the marginal in BC of the original state. And then in this case, Pet's condition is going to read as follows. So the equality between now these two relative entropies happens if and only if we have this expression here, in which of course we are omitting for simplicity tensorizing with identity in A in all these terms, which only have support in BC. Now, if we consider the difference between the relative entropy and the relative entropy after applying the quantum channel, this quantity has several possibilities for interpretation in quantum information theory. One of them, from the point of view of thermodynamics, is the cost of a certain quantum process, as was established by Feist et al. In 2018. And another one, when the quantum channel considered here is a partial trace, it can be seen as a conditional relative entropy, as we showed in a joint work with Lucia and Pérez García in 2018 too. This quantity is interesting for many reasons, and in particular, the data processing inequality, so the fact that the difference between these two terms is always non-negative. This has many applications in quantum information theory, but it's also true that one could think of the possibility of strengthening the term zero that appears in the right-hand side of this expression. So one could think of trying to find a lower bound for the DPI, so for the difference between these two relative entropies, in terms of something that we have just established in the previous slide. So in terms of the Pet's recovery map for the channel T composed with T and applied to the state sigma. And the question, if one can do something like that, has been studied for the past 5-6 years, and many authors have found different possibilities in this line. The first breakthrough in this field, I would say, was given by Fosse and Renner in 2015, where they showed that something similar can be done in the particular case that I was mentioning before. So in the particular case in which now we have a tripartite space HABZ, we have a positive state sigma, and now the second state, rho, is given as a marginal of sigma in BC with the identity in A normalized for the part that we have traced out. And the channel that we are considering in this setting is the partial trace in C. So in this case, the difference between the relative entropies can be written as the so-called conditional mutual information, which is given by this expression here, as we are saying. And what they showed in this breakthrough was that actually you can lower bound the conditional mutual information by the infimum over all possible recoverable state of minus twice the log of the fidelity between the original state and the recovered state. And the fidelity is given by this expression here. This is the first result in this line, but there are many other results. So just to give a bit more information about this result, in particular, if we want to see how we can write this infimum over possible recoverable states, this is essentially considering the PETS recovery map and composing it with some rotation in B on the one side and with some rotation on VC on the other side, obtaining some expression like this one, and then we can lower bound the conditional mutual information by minus twice the log of the fidelity between these two states. After this, many other results follow. We are just going to briefly mention here some of them. So in this case, not just focusing on the particular case of the tripartite space, but for a general framework and for two general positive states and any quantum channel. It has been proven first by Junge et al. In 2015, the fact that you can lower bound the DPI by this integral of some function here, beta sub 0 of t, which we are going to explain now, and the logarithm of the fidelity now between the state and the rotated PETS recovery map of the state of the first state with respect to the second state. So now the rotated PETS recovery map is essentially considering the usual PETS recovery map and having each term in rho rotated accordingly. And the function beta that we are considering here is just something that is close to 0, has big high, and it vanishes when one goes far from 0, it vanishes very fast. Following this result, Suter, Berta, and Thomas Michel were able to prove in 2016 this expression here, which now is a bit more similar to things we are more used to, because now we have here an entropy appearing. It's not the usual relative entropy, but it's a measured relative entropy, which is a supremum over P of EMs applied to both inputs of the relative entropy, which is, so this is going in the line of obtaining something more similar to a relative entropy, but still not a relative entropy. And after that, in 2017, Berta et al. Also managed to prove that the DPI can be lower bounded by this regularized relative entropy that appears here, also with the rotated PETS recovery map. So seeing all these results, the natural question is, can we actually find a lower bound for the DPI for the relative entropy in terms of the relative entropy between the first state and the PETS recovery map applied to the first state? Because it seems like that, but actually the answer is that this is not possible. And this is something that Brandau et al. In 2015 and Fosse in 2017 managed to show just by doing some numerics and seeing that even in the particular case of the tripartite space and one state being given in terms of the other one as marginal or if, this is already false. And moreover, after that, in 2018, Suter and Renner managed to prove also for that setting, for that particular setting, the fact that if you want to find an an inequality between the conditional mutual information and what is called the relative entropy of recovery, which are the two quantities that we are trying to compare here, you need to add some term that appears here as this lambda max, which is something that vanishes if and only if this map RB to B applied to sigma AB gives sigma AB. So if sigma AB is a fixed point of this map, and this map is nothing but the PETS recovery map for the partial trace in C with respect to sigma BC, composed after that with the partial trace in C. So we see that if we want to have like a general inequality between these two quantities, you need to add something that they show in this paper to be optimal. So there's nothing more to be done there. But this doesn't mean that we cannot find a lower bound for the DPI of the relative entropy in terms of the PETS recovery map composed with the channel itself and applied to the first state. And this is something that was done in 2017 by Carlin and Berginina. They did it only for conditional expectations. And here, what they proved was that you can actually lower bound the DPI for the relative entropy in terms of some constants and some multiplicative error terms. But the important part here is the distance measure between the state and the recovery of the state, which is given by the one norm of the difference between these two things. Well, the fourth power of the one norm. And subsequently, they managed to extend these results to standard F divergences. So now the question that appears for us is, can we do something similar to these kind of things for the setting of the BS-entropy? And this is what we have done in this paper. So before proceeding to the results that we have managed to find in this paper, I'm going to introduce some basic notions that we need to understand them. First of all, we need to see what a conditional expectation is. So a conditional expectation between a matrix algebra and a matrix subalgebra of it is the unique linear map that satisfies the following properties. So first of all, it has to be a positive map. Then it has to leave invariant all the states of the subalgebra. And they also need to be able to come out of the map when multiplied by something that in general doesn't belong to the subalgebra. And it's also trace preserving, because these are the kind of conditional expectations we are working on. We are working with, sorry, only the ones that are trace preserving. So only if we only have the properties 1, 2, 3, this is already a conditional expectation. But as I was saying, we are interested in the ones that are also trace preserving. And now coming back to the BS entropy, well, I just recalled the expression that it had in case someone has forgotten it. And let me just remind you also that it's always an upper bound for the relative entropy. Another definition that we also need for the rest of the results to be understood is the notion of an operator convex function, which is nothing but a function that you evaluate on operators and behaves as a usual convex function. So it behaves satisfying the usual inequality that it should satisfy for a function to be convex. Good, so once we have the notion of operator convex function, here I'm going to introduce standard F divergences, which are the first quantities that are going to appear now. And given an operator convex function and two positive states on a matrix algebra, a standard F divergence for this F is nothing but the trace of rho 1/2 and F of this term that appear here, and again rho 1/2. And this term that appears here is essentially the left multiplication by the state sigma and the right multiplication by the state rho -1. So in particular, when we consider F to be x log of x, we obtain back the relative entropy. So this is why standard F divergences are nothing but a generalization of relative entropies. And since the relative entropy we knew that satisfies the data processing inequality, actually what we can see is that any standard F divergence satisfies a data processing inequality. Moreover, concerning the data processing inequality between for a standard F divergence, one can think of when there are conditions, well, which are the conditions for equality in this data processing inequality. And this is something that we present in this result here. So there are many other equivalent conditions that are presented in this paper of Hiei and Mosoni of 2017. But here we are only interested on the 3 that appear, that we write here. So essentially there's equality for the data processing inequality for standard F divergences if and only if there exists some recoverability, some recovery map that allows you to recover both the first state and the second state, and also whenever this can be taken as the PETS recovery map for the channel T. So it's really a generalization of the result that we already saw for the relative entropy. Good, so now we can move to the setting of maximal F divergences, which are more or less related to the ones that we have just presented. And again, for operator convex functions, maximal F divergence is defined in this way. So it's the trace again of ρ1/2 and ρ1/2 in the left and the right part. And now inside the function, so the function we are evaluating it now in ρ-1/2 sigma and ρ-1/2. And again, if we consider the function x log of x, now what we get back is the BS entropy instead of the relative entropy. So as we were saying before, the BS entropy is always majorizing the relative entropy, and this is something that also happens for the relationship between maximal F divergences and standard F divergences. So first, let me just say that the data processing inequality also holds for these kind of quantities. And as I was saying, there's also the inequality that we could expect for the same operator convex function between maximal F divergence and standard F divergence. So now if we review conditions for equality for maximal F divergences, we also have a number of conditions also presented in this paper of Hiei and Mosoni of 2017. But the problem that we find is that even though there are a number of conditions that might be interesting for several reasons, there's none of them for which we have an explicit expression for the recovery of sigma in terms of anything else as we had for the case of standard F divergences. So this is something that we feel that we are lacking here. So now we have 2 questions that we are considering in this project. One of them is, as I was saying, there's not explicit expression for the recovery of sigma. So can we find something like that for the BS entropy in particular, or for maximal F divergences in general? And the second question is, once we have some recovery condition of this kind, can we provide a lower bound for the DPI of the BS entropy in terms of it, following the lines that Carlen and Berginina already introduced in 2017? And the answer for both questions, we're going to see that is yes. So this is what we are going to show now. First of all, let me just call gamma the product between sigma minus 1/2 rho and sigma minus 1/2, and the same for gamma t, where all these terms that appear with the subindex t are essentially after the application of the channel to each one of them. So the first result that we have proven in this paper are some equivalent conditions for the equality on the DPI for the BS entropy. So essentially what we prove is that after applying a quantum channel between 2 matrix algebras, we have equality for the BS entropy. So we have equality for the DPI in the BS entropy, sorry, if and only if one state can be recovered in terms of the other one by this expression that we write here. So now this is an explicit expression of them. And also if some other equality holds, which is something auxiliary that we need for the calculations of the rest of the proofs. But the important one here is the second property, which is what we call the recovery condition. So now, from now on, for us, the BS recovery condition for the channel T with respect to the state sigma is given by this expression here. And this is something that we are going to compare with the PETS recovery map. In our case, we don't call it a BS recovery map or whatever, because we are leaving the recovery maps only for those maps which are recoverable, which recover states in the same sense that PETS already introduced in the 86. So essentially, for all of them, the set of fixed points is always going to be the same, and for ours, it's going to be different. So this is something that we're going to see right now. So we can see, as a consequence of this result, we can see a couple of corollaries which essentially were known before, but now they are easier to follow up from our results. And one of them is that we have equality between, well, we have equality in the DPI for the BS entropy when the first input is sigma and the second one is rho. if and only if we can reverse the two inputs of the BS. And this is something that is very easy to see after writing explicitly rho in terms of sigma here, or the other way around, writing explicitly sigma in terms of rho here. And the other condition that we find as a corollary from this result is that we have equality in the DPI for the relative entropy, and then this implies that we have equality for the DPI in the BS-entropy, but not the other way around. And this means that one state is PETS recoverable. This implies that one state is BS recoverable, but not the other way around. So the converse of this result is known to be false. And a couple of examples, explicit examples, can be found in these two papers mentioned here. So this is why I said that since the set of fixed points of this map here is bigger than the one here, this is why we cannot call this map in the same way that the one that appears here. After that, the second objective that we were following here was to provide a strengthening of the data processing inequality in terms of the difference, in terms of some distance measure between a state and its BS recovery. And this is something that we managed to do in a similar way to what Carlen and Berginina did. So now what we managed to prove was this lower bound for the DPI for the BS entropy in terms of this quantity, or in terms of this constant, this multiplicative error terms, and the true norm now of the fourth power of the true norm between a state and the BS recovery. And this, to prove it, we just had to follow some steps. So first of all, we proved it for quantum channels. So before doing it for quantum channels, we restricted to the case of conditional expectations. And we proved this lower bound for the difference between BS entropies in this case, in terms of the auxiliary quantity that I was mentioning before, in the result of equivalent conditions for equality and the DPI. Then in the second step, we managed to find a lower bound for this quantity in terms of some multiplicative error terms and the quantity we were interested on, so the difference between the state and its BS recovery. Now it's simpler because this is just a conditional expectation. And of course, after that, we had to lift our results to the case of quantum channels just by using Stein-Sprint dilation. So for the first bound, we found an analogous bound, which shows here the presence of V and V star, where V is the isometry that appears in the statement of Stein-Sprint theorem. And in a second step, we just lower bounded this quantity by the analogous quantity showed before, and now with the usual BS recovery condition for any quantum channel. So this is what we did for the BS entropy. And as I was saying before, since maximal F divergences are just generalizations of the BS entropy, one could expect that these results could be extended to that framework, and this is something that we actually managed to do. So in this case, the situation is a bit more subtle. Now we cannot do it for every operator convex function, but we can do that for operator convex functions which satisfy a number of conditions. And we see that in this case, we get some lower bound for the difference between, well, for the DPI essentially of maximal F divergences in terms of a number of multiplicative error terms. And again, the same difference between a state and its BS recovery. But now there's a presence here of some quantities depending on a parameter alpha. And this alpha is essentially something that appears only in the Radon-Nikodym derivative between the transpose of the operator convex function with respect to the Lebesgue measure. So this is a summary of the results that we obtained here. And I just compare them briefly to what was obtained previously by Carlen and Berginina. So we see here, well, that the PETS recovery map and the BS recovery condition can be easily compared in the sense that this is kind of an asymmetric version of this one. So of course, if everything commutes, everything here is the same. And the problem appears when things don't commute. When things don't commute, what we know is that the set of fixed points of this map is greater than this one, in the sense that it contains the set of fixed points of this map and is extremely larger. And once we know that, we proved a similar lower bound for the DPI. In their case, it was for the relative entropy, and in our case, it's for the BS entropy. But we see that they only proved it for conditional expectations, and we managed to lift our results for quantum channels. But I mean, this is something that they could also have been done easily. And after that, of course, they extended these results to standard F divergences, which is also something that we managed to do in our analogous case to the framework of maximal F divergences. So let me just conclude this talk with some future work. Again, we're going to consider here the particular case of HABZ as a tripartite space, and we're going to consider as a quantum channel the partial trace in Z. So now if we again consider the state rho given as a marginal of sigma, properly tensorized with the identity in A normalized, then again, as I was saying before, the condition for the PET's recoverability is written in this way, and the condition for the BS recoverability is written in this form, which looks a bit simpler, but again, it's just some asymmetric version of this one. So now, as we were seeing before, sorry, this equality here implies that there's equality, that the second expression holds. But the reverse, in general, we believe it to be false, because we know that there were some counterexamples between equality in the case of BS recovery map and equality in the case of PET's recovery map. The problem is that the examples that were presented in the past were for situations in which, of course, rho and sigma were completely different one from another. So in this particular setting, as far as we know, there's no previous example of, well, there's no previous counterexample for this arrow here. So one interesting problem we are currently working on is providing an explicit example of a quantity that satisfies this expression, but not this expression here. And once we have that, an interesting question that arises is the set of BS recoverable states, so states that satisfy this condition here, is this set robust in the sense that if we have something that is close to satisfying this condition but doesn't satisfy it, does it mean that it's close to being a BS recoverable state in the sense that the analogous to the conditional mutual information, but for the BS entropy would be small? And this is something that we are also currently working on. So with this and showing briefly the bibliography that we have mentioned in this talk, with this I conclude. So thank you very much for your attention.